Hey all, it's Andrew Couch here, and in this Tidy Tuesday video, we're not going to be looking at this week's dataset. Instead, I wanted to start a series where I focus on learning neural networks, specifically using the Keras library. The reason why I like Keras over using things like TensorFlow or PyTorch, or in this case Torch, is because I like Keras's like interactive or more um, uniform interface. I think Keras is kind of like the tidy models of neural networks. And additionally, Keras actually is the front end of TensorFlow. So you're basically using TensorFlow, but you have a much more simplified interface. So I thought one interesting video would be using the LSTM text generation example. And I'm not gonna write out the entire text generation model. Instead, I'm just gonna use their direct example and use our own data for it. And I think this is kind of a good idea because that way we can focus more on getting some intuition of like what we're actually trying to do, or how do we even load this data into a neural network to actually generate text. So with the text that we're going to generate is some Trump tweets. I thought it was kind of interesting to do your own text. And since there's a Trump Twitter archive, I downloaded all of Trump's tweets since yesterday. So let's open up my R Markdown file, and I actually already pasted everything in. So I figured this video would mostly be a walkthrough instead of actual coding, but I think that's pretty important, and it's a good introduction to the main ideas of neural networks. So I'm just going to load in my packages. In this case, we're going to load in Keras, Tidyverse, and tokenizers. So Keras is obviously the package for our neural network architecture that we're going to be building. Additionally, we're going to just use Tidyverse because I want to use some stringer and do some data manipulation stuff to the text. And then we're going to use tokenizer, which is actually going to convert our table of text into a list of text. And one thing with neural networks is you're basically going to be doing a lot of list manipulations. So you're going to be using like a lot of like sapply, mapping functions, etc. So we loaded in our libraries. I'm going to load in our text. And our text is actually pretty clean. It's just one column full of text. So what we're actually going to be making is a character level text generation model. So I'm going to do some basic regular expression cleanups. So for example, this thing right here is going to eliminate most of the links. Right, this command will make it into lowercase. And then this command right here is essentially removing anything besides lowercase letters, a period, or white space. And then it also uses this to remove the -n and -r. So if we actually run this part, we can see that we basically removed all the weird numbers and we just have pure letters and spaces. I then will pull the text, which will basically grab all this text and convert it to a list. I'll use SCR to lower just in case I did anything crazy. And then I'm going to basically collapse it using the -n. And lastly, it's going to tokenize the characters. So it's basically going to split all of these sentences into letters. There'll be a list of letters for every observation. We're going to run that. Okay, we can print that, and we can see our corpus length is, what is it? 4,780,000 tokens long. I'm also going to use it, grab the text, and grab all of the unique characters, and this will essentially be our character library or dictionary that we're going to reference as like an index. We're also going to specify the max amount of characters that we're going to be using. So in this case, I'm going to just say 15 characters. So we're going to use 15 characters for our model. The next thing right here is basically the main idea of how we're going to make a text generation model. So this looks kind of confusing. What it's essentially doing is it's obviously with the comments, it's cutting these semi-redundant sequences to the max length of characters. So essentially what it's doing is it's taking these words or these sentences, taking 15 characters out of it, okay, and then taking one character out of it at the end, and then having it predict that character. So I'm going to run this. Additionally, it's going to do some data manipulation so we can do more vectorization to it. So the X character will be the characters that we're going to use. And then the Y is the next character that we're trying to predict. And this will basically convert it to ones and zeros using our dictionary. So I'm going to run this, and hopefully I won't run into any memory constraints. The big problem with actually doing neural networks is basically trying to figure out what type of data we can, how we can manipulate the data so it'll fit into a neural network. Neural networks essentially want zeros and ones or anything in between. So I'm going to show you just a basic little intuition of what we're trying to do using matrices. I'm actually going to put my R markdown thing to my left just so I can keep track of it. Okay, so this is basically the matrix that we're using. So we have 15 characters that we're using. And then for each character, we have these characters that could be in this position. Okay, so this is essentially the dictionary. And we're basically saying, like, okay, so if I were to type in like the, and then be space, cat, you know, et cetera, it would essentially be like ones and zeros. So it'd be like a one would be right there. The rest would be zeros. A one would be right here. So it kind of reminds me of like, was it the like ITBS or the bubble sheets, right? The bubble sheets where you're taking your midterms. So using these like essentially one hot encoded vectors or matrices, we're basically trying to predict what's the next character, which will be this single little list. So that's basically what it's doing. And using neural networks, it'll basically say, okay, we've seen the cat, I'll say like is, and it'll say SMAL. So it's saying like the cat is SMAL. And then what we're trying to predict is L, right? This is what we're trying to predict. So it'll basically use this, train it. It'll say, okay, well, our next character should have been an L. So we'll go back and we'll reshuffle again and keep on trying to predict it. So it's just using these past letters to predict the next letter. Okay. I think our thing completed. So let's actually create our model. So in this case, we're making a basically a single layer LSTM model. So we initialize our Keras model and we start adding our layers. So this is our first LSTM layer. We're going to say that our input shape is our max length by the length of characters. What this is essentially saying is what we want, what we're inputting is this. So it's saying it's 15 characters by our total dictionary or total available characters that we could even use, right? So it just has this little matrix that we're trying to throw into it. And even though this is like essentially a two-dimensional matrix, right? Because it's not like a list, it's a square. What's cool about neural networks is it can use multi-dimensional matrices. So unlike shallow black box models, where it's essentially taking tabular data, or essentially a list of data. So it's taking like, okay, we have this, and we're trying to predict that. The neural networks can take 2-dimensional, 3-dimensional, or even 4-dimensional and up. So we're just saying like, this is what our entire input is, which is like the available characters that we're trying to do, or like the one hot encoded matrix. And then when we're saying we want our output nodes from this to be 128 nodes. Then we're doing a final layer, which will be our output layer. And this output layer will be the available characters that we're trying to predict. So let's say like, okay, so what's the probability that the next character is an A? What's the probability of it being a B, etc. So that's why our last layer has to have the output to be the length of our characters or the total number of unique characters we can use or predict. Then we use a softmax activation function, which is basically how it can compute that probabilities. We have an optimizer, which is optimize our RMS prop. Generally, people will use Atom. In this case, the example just uses RMS prop, and then also use some regularization. Lastly, when we compile it, we use categorical cross entropy, and this is the loss we use for multi-class classification. if you were to do a specific binary, you do like I think binary cross entropy, etc. So now let's actually go to these functions that they added. So first we have this sample mod function. And what these functions essentially do is that they're trying to use a random letter to feed it into the model, and then using that model to predict another letter. And then it takes those two letters and puts it back into the model to predict another letter. So it's kind of this recursive sequence where it's essentially predicting, using that prediction as an input and predicting again. So with this temperature, basically, if we can look at it, temperature essentially affects how variable the predictions are, and uses like R multinomial distribution to figure out a random number to use as the input input and outputs of the letters. And then on epoch or epoch n, it's essentially going to train the model, and then for every epoch or epoch, it's going to basically run the sample mod function and generate some text for every time it runs. I actually did forget the last model fit, so let's do that. So we're going to run that. And now we can just paste this in and run it. So I'm just going to, what's print callback not found? Oops, I forgot my print callback, which would be that. So I'll throw that in right there. And then it's going to start training. It's also cool is it might be throwing out a plot sometimes, but I guess it's just going to do this. So right now, when we're fitting using the input text data or input like matrix. That's essentially the one hot encoded two-dimensional vectors. And then we're trying to predict using one list, which is the available letters that we can predict. We're using a batch size of 128. So essentially, we're just using 128 tweets, and then we're letting the model look at it, letting it learn what it's supposed to be predicting, and then we're going to send another batch. And it's going to keep on doing that until we basically went through our entire data set. So in this case, we have about 39,000 or 40,000 tweets. So it's going 128 out of the 40,000 tweets, training it and going through it one time. And as you can see, it's going through it pretty fast. So I'm going to just go wait a little bit, but I figured I also could go over a little bit more about Keras and some resources that I really like. So for example, Keras is pretty straightforward. They have a lot of great tutorials. The best tutorial probably, or the biggest intro tutorial, is the fashion dataset or the MNIST dataset. I've actually made a video on doing the MNIST dataset where you basically classify handwritten numbers. But our studio's TensorFlow page is a pretty good guide about learning just how to do neural networks, specifically with transitioning from like your traditional usage of data frames to tensors. Additionally, I would also recommend Deep Learning with R by like Francois Cholet, which is actually the creator of Keras. So he has a great book about how to use R and also the intuition between all of these models. So not only just doing your simple neural networks, but also getting into convolutional nets, LSTM nets, recurrent neural networks, etc. I will say that when do you actually use neural networks is dependent on your use case, which is, so I would say that generally, if I'm looking at like say the Penguin data set, I won't really go into neural networks because neural networks seem to be overkill. You also need a lot of data for it, and it doesn't add that much business value besides just only predictive power. A good use case for neural networks is with things where you need to create a lot of features. So things like images. Images are very hard for black box models to understand because you have high dimensionality. Because when you're looking at images, you're essentially analyzing every pixel and its pixel value, so it can be RGB. And in that case, neural networks are great with high dimensional data, and they're good at creating basically features that we want to understand, like curves. Additionally, sometimes neural networks are really good with highly imbalanced data. So if your class that you're trying to predict is like 99% imbalance, where 99% of it is negative, 1% is positive, a neural network would be good at would be good for that problem, specifically autoencoders. And I really want to make some more videos on neural networks, so I'll probably make a video on autoencoders soon. But autoencoders are always a thing that I think about when we have, you know, high class imbalances and a lot of data. So using autoencoders for sensor data for anomaly detection is basically one of the main uses for them. Let's see here. So I'll probably stop the video and resume it when this model is done fitting. Okay, so the model finished training, and we can see the generated text. So for example, it uses a diversity of 0.2, and we can see the communities and the Democrats are the fake news, is the Democrats, and the last night of the Democrats are starting, and the country and the many with the etc. So you can see how most of this doesn't really make any sense, but it's pretty interesting because it's honestly making something that resembles like an understandable sentence. And if anything, we can understand, what are the words that he's using a lot that this model is kind of like learning off of. So as we increase that diversity, we can see that the words are more diverse, right? So we'll be all to bust at the present, real, middle, big people, to be, and has lived. So you can see it's getting a little bit more diverse, but it's losing a lot of the actual readability of it. And then we can see it keeping it's still going, and it's basically just gibberish. So things that we could actually improve off of is just running it more times. So if we increase the epochs or epochs, we could probably get a more legible, more readable dialogue. I also have this function that I found off of, I believe, I think Julius Silly's website. So this function will be using our model to generate phrases. So let's actually go through it. Generate phrase. It uses a model, a text, a chars. So I'll give it model, our text, our chars, our max length, and I think it gives us our, our diversity, I think. Generate phrase, diversity. So diversity is equal to, let's say, 0.5. So we can see it generate. And it's going to take a while because it's recursively trying to predict on itself, but that'll take a little bit. So all but will be and the people and should be assigned to the be. So starts to the documents. So it's talking about documents. It's going to be talking about Democrats. Let's run it again to see if it'll generate a new text. Yep, so it generated some new text and a support out to Rombers and the press, good many president and the country and the Democrats, etc. So this model can definitely be improved by running more epochs. So you may also be wondering, like, why don't we just use a word level model? And that's a pretty good question. The main issue with word level models is that you are dealing with a larger array of words than letters. So since we're only using letters, there's only about 26 to 28 characters that we're going to be using, because we're including spaces, periods, and maybe even commas and apostrophes. So at max, that's about 30 characters that we're actually going to be having to remember. Opposed to actually using tokens or words, we can see how it can expand a lot, because generally people use a relatively diverse amount of words. So that could be ranging from 1,000 to 5,000 words. And when you have that, your matrix gets very large. And additionally, you're going to start running out of memory. So since we're actually creating these data sets and storing it in memory, your computer or R can't exactly handle these data sets because they're too large. Which really kind of leads us to, how can we handle data sets that fall out of memory? And that's what basically leads to batch training, where you're essentially gonna take a little chunk of the data, run it through this little pre-processing stage, then giving it to the model, and keep doing that until we went through our entire data set or one epoch or epoch. So that's one problem with using a lot of these word level models, is that character level models are generally easier to implement because we have less dimensionality issues. And what's interesting is character level models are pretty good at basically creating somewhat understandable sentences in words. See, for this, we never gave it words. We only just gave it the letters to predict. And it was able to actually make some pretty good understandable words, and honestly, some pretty good sentences. So I know this is a pretty quick video, and I know we didn't do a lot of coding, at least for myself, but I think this is a pretty interesting thing to do, just kind of doing a code review of the Keras example. So I'll see you guys next week, and tidy on.